because the originally second speaker, Professor Wang Yidun, has a schedule of flight. So we changed the title and the speakers of the second part. The second part will be given by Dr. Ching-Yu from Stony Brook, and she will be speaking about the classification of topological ordered faces. Let's welcome her.
Thank you. At first, I would like to thanks for the organizer and for the nice conference. And I think if you have any question, please feel free to ask question at any time. So today I will talk about the classification of the topological defects. So this is my outline. First, I will give some introduction about the phase transition and the topological defects. And then I will show you two works. The first work is a symmetry protective quantum state renormalization group. And the second work is about the detective symmetry enriched topological defects. And finally, I will give you a summary. Okay, so let me start. So we know the muscle phases can be understood by Landau symmetry breaking theory. So for example, for the crystal, we have an array of atoms. So sometimes it breaks the translation and the rotation symmetry. And another example is a magnetic. We know the magnetic has a source and the source part, so it breaks the spin rotation and the time reversal symmetry. So we can ask the question, how to classify the different phase and the phase transition. So we can see an example is a two-dimensional ice model with a magnetic field. Once we turn on the magnetic field, we can find the phase transition from the ferromagnetic field to a paramagnetic field will occur. Then we know the maximization is the order parameter. So we know the local order parameter can be used to capitalize the different phase and the phase transition. And however, we know that in the 1980s, the new phase, the fractional quantum Hall effect, was discovered. And it cannot capitalize by the Landau symmetry breaking theory. So it's beyond the breaking theory. And it's against any small perturbation, so they call it the topological defects. Then the topological defects have several amazing properties, such as it can be capitalized by the ground state degeneracy on the torus, and it has a fractional statistic of the quasi-particle, and it can detect it by the topological entanglement entropy. Then we know the well-known example is a two-dimensional torical model. It's the ground state of the torical is the equal wave superposition of all closed loop. So we see when we choose a block, we can find the crossover points always even. So it shows this phase has a long-range entanglement. So we know the long-range entanglement also can be used to classify the topological defects. Okay, so now we want to ask a question: how to classify the different phases. So we follow the idea the long-range entanglement. So sorry. Okay. So we know that for the gap system, when quantum phase transition occurs, then the energy gap will cross. So assume we have two quantum states, the psi 1 and psi 2. Then if they are connected by the adiabatic evolution and without cross the energy gap, then we can say those two phases below the same case. So or we can say if those two phases related to by a local unitary transformation, then those two phases below the same case. So from this case, we know that we can use a local unitary transformation to classify the different phases. Okay, so from the local unitary transformation and the quantum information viewpoint, so we can use the local unitary transformation to classify the all phases. So apply the local transformation, all facts can be divided into two parts. The one part is the short-range entanglement. That means when we apply the local unitary transformation can remove the short-range entanglement. So the short-range entanglement means if we apply the local unitary transformation, then the original wave function will flow to a product state. And another part is the long-range entanglement, or what we call the topological order phase. However, if we consider the symmetry, so we know that means if we apply the symmetric local unitary transformation, then we know that there are more kind of cases. So for the short-range entangled state, for some phase have a special pattern of the short-range entangled state, and this short-range entangled state preserved by the symmetry. So they call the symmetry protective topological defects. However, for the long-range entangled state, the symmetry will enrich the long topological defects. So they call it the symmetry enriched topological defects. So in the following, I will give you an example how to numerically how to classify the symmetry protective topological order phase and the trivial state. And another case is how to classify the different SET phase. Okay, so the method I use is mentioned by the Zheng Chen. I use a tensor product state. So actually, because we know that for the many-body system, the important question is how to represent the wave function efficiently. So the one way we can do is we can decompose our coefficient into the several tensor network, and this tensor network just depend on the small number of properties. So this method is a tensor product state. So in the following, I will use, for 1D, we use a metric product state. For 2D, I use a tensor product state as a to starting the function state. Okay, so let me start my part 2. So this work, I work with Xie Chen and Professor Feng Lilin. Okay, so in this work, we want to starting the symmetry protective topological order phase. Then we know the symmetry protective topological order phase actually is a trivial state if we just apply the local unitary transformation without preserved symmetry. It will flow to a product state. However, if we apply the symmetric local unitary transformation, such as we preserve the isotropic symmetry, and it will flow to a non-trivial fixed point. So we call it the symmetry protective topological defects. The well-known example is the topological insulet and the Hoden phase in the one-dimensional, in the spin one chain. Okay, so in the following, I will starting the symmetry protective topological defects. Okay, and then I think we would like to ask a question: how to detect the symmetry protective topological defects? We know that in the Frank Pullman's work, they measure the projective representation, and here I would like use another way. We know in the Xie Chen's work, they propose a method called quantum state renormalization cube to distinguish the topological order phase and the trivial phase. So we would like based on this idea and generalize this to the symmetry protective topological order phase. So here I will just quickly show you what the method proposed by the Xie Chen. They start from the sum wave function, and it's represented by the tensor product state, and they do the quantum state. I call it quantum state RG to remove the short range entanglement, and flow it to the fixed point. And then we measure some environment quantity. For here, she measure the F2 divided by S1, just some number. And then we can see the phase transition from the trivial phase to the topological order phase. Okay, so here we would like to generalize this to the symmetry protective topological order phase. Okay, so we know that the usual RG is the co-squaring of a block of a degree of freedom in the Hamiltonian. So we can obtain the effective Hamiltonian. But for the quantum state renormalization group, actually we start from the some wave function. It can be represented by the tensor product state or metric product state. And then it contains the two steps. The first step, we apply some local unitary transformation to remove the short-range entanglement. And then the second step is co-squaring. We merge two signs to obtain the effective wave function. And then we know that for the one-dimensional system, there is no intrinsic topological order phase. So that means that all of one-dimensional state will flow to a product state. However, as I mentioned above, if we consider symmetry, if we preserve symmetry, then it will flow to a non-trivial fixed point. So in the following, I will show you the method. I will show you a method how to determine the symmetric local unitary transformation automatically. And okay. So at first, I start from the one-dimensional AKLT phase. Why we start from the one-dimensional phase? Actually, the one-dimensional quantum strategy was proposed by the versatility, and it just merged two signs, and it can work well. However, it's hard to generalize to the higher dimensional system, so we just start from the one-dimensional system. Okay, so I start from the one-dimensional AKLT, and the one-dimensional AKLT is Van Spong solid. It's connected to the nearest neighbor site, and and if we just merge two signs, and it will flow to a fixed point. So the fixed point is a diamond state, or we call a Van Spong crystal phase. However, if we do the real quantum strategy, that means we apply the local unitary transformation to remove the short-range entanglement and do the co-squaring. So it will flow to a trivial state. However, if we choose a particular local unitary transformation to preserve symmetry, for example, for the one-dimensional AKLT, if we preserve the SO3 symmetry, then it will flow to a non-trivial fixed point. Okay, so here I will show you the procedure, the symmetry protective quantum state RG procedure. So the first procedure is the first step. We merge two signs to obtain the two sign double tensor, and we splitting it to up and down row, and we can get a new tensor A tilde. And the important thing is we need splitting it into the two parts. So here for the symmetry protective quantum strategy, the important thing is when we splitting the physical dimension I into the S1 and S2, we need to make sure the Si and S2 in the correct projective representation. For example, the half integer and the integer is a different projective representation. So for the AKLT, one-dimensional AKLT state, we need to make sure the S1 and S2 must be in the integer representation. And then we So if not, we need to apply some local natural transformation to make sure the S1 and S2 in the correct projective representation. And then we splitting it into two parts. Until this step is disentanglement, we remove the short-range entanglement. And the next part is cross-graining. We merge two sides and to obtain the new metric. Okay, so follow this procedure. We start from the one-dimensional AKLT and the one-dimensional dimer state. It will flow to the same fixed point, and this fixed point is not product state. So that means the one-dimensional AKLT and the one-dimensional dimer state below the same case. Okay, so and then we would like to.
What do you do in the second step?
Sorry.
What did you do in the number
you
two?
mean the second?
No,
here?
number two. Yeah.
Here we just because here we subtract the physical dimension. Okay, so here it actually is the virtual dimension, and then we splitting our tensor. We do the SVD around this direction. So we have alpha, gamma, and alpha prime, gamma prime. So when we do the SVD around this direction, we can get a new physical dimension. So in this step, actually, we just need to get the new physical dimension. And then in this step, we need to make sure the the S1 and S2 in the correct representation. Okay, so it can work well in the one-dimensional system, and then we like generalize to the two-dimensional system. Okay, so we starting the two-dimensional AKLT step. So we consider a spin 3/2 module on the honeycomb lattice, and then we consider the Hamiltonian like this term with the parameter J2 and J3. And in particular, at this point called the AKLT point, this wave function, this Hamiltonian is the exact solvable model. So we can write down the wave function exact, and this one state can be represented by the tensor product state with the bound dimensional equal to 2. And in the following, I would like to do two things. The first thing we would like to starting this Hamiltonian. And then the second thing is we would like to start from the AKLT point and flow it to the fixed point to make sure this phase is a SPT phase or not. Okay, so here is we generalize the one-dimensional quantum state algae to a two-dimensional quantum state algae. Then here the two-dimensional quantum state algae also contains the two steps. The first step is the disentanglement or remove the short-range entanglement. We can see if the two sides with one singlet, and when we merge two sides and splitting around another direction, then we can find the singlet was removed. So this is why we can say this step remove the short-range entanglement. And then is the first part we splitting a tensor around the different direction. So this step is disentanglement. And the second part is cross-graining. I take the example is the honeycomb lattice. So we can get a new tensor to meet as a triangle to get effective tensor. So this until this step is the original quantum state RG. I think that this one is similar to the TRG. So the different things is when how to preserve the symmetry. So when how to make sure. So in order to preserve symmetry, we need when we do the splitting the tensor into two parts, we need to make sure the J1 and J2 must in the correct representation. So this idea is similar to the one-dimensional system. So we need to apply some local natural transformation to make sure this is in the same case of projective representation. Okay, So, so and then we starting the two-dimensional AKLT, and I use the cancer product stem answers with the 6 impurity cancer, and I use the simple update to obtain the ground state, and then I calculate some local order parameters such as the magnetization and near order by using the cancer remonetization good, and then we can get the full phase diagram. And in particular, I choose the special case. In this figure, I choose J2 equal to 0.1, and then we can find for some region, all of the local unitary transformation, all of the local order parameter would be 0. So it could be a topological defects. So, and then, okay, so I plot the figure to show the phase diagram. So in this region, the local order parameter would be 0. So I say that this could be a topological defect. And then we use a quantum state RG without preserved symmetry. So we find if we did not preserve symmetry, and all of state will flow through the product state. So that means all phase is a short range entanglement state. However, if we preserve the symmetry, then we can find in this region, the AKLT phase will flow through a non-trivial fixed point. So this is evidence for the symmetry protective topological phase.
What's the gray region?
The green.
Gray. Yeah. What's the phase?
Because we can see the I calculate the near order and the ferromagnetic order is not 0. So actually I don't know what is this phase. Yeah.
So excuse me, the AKLT phase is protected by what symmetry?
I preserve the SO3 symmetry. And
SO3.
yes.
And so, but the name AKLT in 2 dimensions, do you also require translation symmetry?
I think it's because the answers I use, I think the preserve the translation symmetry.
Yeah. So there's an issue that
So you mean
whether translation symmetry is a key. Actually, SO3 may not be. And
okay,
but also there's an issue that this cancer renormalization seems change translation symmetry in some way. So whether there's enough translation symmetry so that we can see AKLT states.
So yeah, actually I preserve. So
the difference is following. The SO3, 2-dimensional SO3 SPD phase without translation symmetry have a quantized Hall conductance. This is SO3 Hall conductance. But however, the 2-dimensional AKLT states do not have a quantized Hall. So there's a difference.
I see.
And I wonder whether one can see this difference.
I think here,
Please.
for calculation-wise, you can only get the simple translation.
Yeah, but the issue is that whether these answers describe SO3 SPD phase or AKLT SPD phase.
But because we actually just looking, in some sense looking at the H state, which has right projective representation. But the key is the calculation. If we change, for example, we practice, we change different representation.
The issue is that whether your answers at the end have a quantized spin Hall conductance or quantum spin Hall. I don't know which way. Which.
So let me break the summary about this work. So I try to use quantum state RG as a numerical tool to studying the SPT phase by using the metric product state and the tensor product state. And the key point is preserve the symmetry when we do the quantum state RG. And we consider one-dimensional and the two-dimensional AKOT phase as an example. And in the future, I think we can generalize the quantum state RG to the SET phase, or we can generalize this one to the quantum diamond model. And this one is just a simple calculation. I start from some trial wave function. It's the RVB phase and the Coulomb phase. The RVB phase is the equal weight superposition of all possible configuration of a diamond. And then when we tune the G, we can find some phase transition from the trivial state to the V2 topological order phase. So by using a quantum state RG, we can find the transition point. And here I put my wave function in the long field, so we can get the reduced density matrix. So we can get the topological entanglement entropy gamma, but it seems hard to determine the transition point. Okay, so in the second part, I will talk about how to detect the symmetry enriched topological order phase. And this work is work with Xuechen and Frank Homan. Okay, so we know the topological, as I mentioned above, the topological order have several amending properties. The one of them is the topological degeneracy. And the topological degeneracy depends on the topology of the space. So the ground state degeneracy, the number of the ground state is related to the n the power of g. So for the g is a genus or a number of the handle. So for the sphere, the g equal to 0. For the torus, for the g equal to 1. So for example, for the Finite number equal to 1/3 fractional quantum Hall effect. So it has a threefold degeneracy on the torus. And for the V2 liquid, it has a fourfold degeneracy on the torus. And it can be distinguished by the even and odd widening number around the two cycles. And another property is the quasi-particle statistic. So we know the different topological order phase given us different quasi-particle with different statistic and the charge. So we know the topological order phase can be capitalized by the quasi-particle excitation, or we say the braiding statistic. So for example, if we consider some wave function sign, and for the fermion, if we exchange our quasi-particle, we can get the trivial phase factor. But for the fermion, we can get the phase factor -1. And for the abelian annual, once we exchange the quasi-particle, we can get the non-trivial phase factor. And for the non-abelian annual, the ground state is missing. So once we exchange the quasi-particle, then we need to use a matrix